So in order to define properly this point at infinity on the elliptic curve, we have to first talk about the projective plane. So we'll define the projective plane first. So you can think of starting with three-dimensional space and viewing every straight line through the origin as a single point in the projective plane. This gives us a two-dimensional set of equivalence classes. There's two types of points in the projective plane. There are finite points and there are infinite points. And it's from this collection of infinite points that we get our point at infinity on the elliptic curve. There's a nice spherical model, a way to think about what the projective plane looks like, a set of points on a hemisphere, where the points at infinity are the points along the equator. Now, in order to define curves in the projective plane, you'll have to start with a homogeneous polynomial. So I want to talk about what it means to homogenize a polynomial. And then we'll take a look at some examples of curves in the projective plane, and in particular, look at the elliptic curve and how we get the point at infinity. Okay, let's make precise this concept of a point at infinity. So to define the projective plane, we start with Euclidean three-dimensional space, delete the origin, and define an equivalence relation by saying 2 points, x, y, z, and x prime, y prime, z prime are equivalent, so tilde here for equivalent, if there exists a non-zero scalar lambda in the real numbers such that one point is a scalar multiple of the other point. That is, the 2 points lie in a straight line through the origin. So the real projective plane then is the set of all equivalence classes with respect to this equivalence relationship. And the way you denote equivalence classes is like this. You take your set, R3 minus the origin, mod out by tilde. So we denote the elements of the projective plane using colons. So A colon, B colon, C colon. So for instance, 1 colon 2 colon 3 is the same point as 2, 4, 6, and it's the same point as 3, 6, 9. All of these are scalar multiples of one another. Now to distinguish the ordinary plane of points from the projective plane, we sometimes refer to the ordinary plane of ordered pairs as the affine plane. So you have a projective plane and an affine plane. So there's two types of points. We have finite points and infinite points. So any point in the projective plane where the third coordinate is not 0 is called a finite point. And because the third coordinate is not 0, you can simply scale it down to make the third coordinate equal to 1. So every finite point has a unique representative and where the z coordinate is equal to 1. And so you can identify the finite points with the two-dimensional plane z equals 1 in the affine space R3. So let's just draw a picture of that. So this is the ordinary three-dimensional space, x, y, and z. And then up here we have this plane where z is equal to 1. Like that. And just think of it as sitting parallel to the xy plane down here. Sitting up here parallel. Z equals 1. And if you give me any point, let's see, we have a point up here, ABC, capital ABC, where C doesn't equal 0, you can scale it down, so draw a straight line through the origin. At some point it penetrates this plane, and so you scale it down, and here's a point, A over C, B over C, 1. And so in the projective plane, A, B, C is equivalent to the point A over C, colon, B over C, colon, 1. Okay, so those are the finite points. You can just think of them as being this plane Z equals 1 up here. And then there's points at infinity. These are points where the third coordinate is equal to 0. Okay, so when the third coordinate is 0, you're down in the xy plane, and you can then scale those points down. So if the y coordinate is not 0, you can scale it down and make the y coordinate equal to 1. So you get a collection of points down here where y is equal to 1. Yeah. And these would be points at infinity. And then there's one point where z is 0, y is 0, and then a would have to be a non-zero number, and you can scale it down to 1. So you get this singleton point. So altogether, the projective plane you can think of as this two-dimensional plane, and that's where the name plane is coming from, together with this straight line right here, and this singleton point right here. And these points down in the z equals 0 plane we'll call points at infinity. There's a nice way to put together those three different components, and this is called the spherical model of the projective plane. So we identify it with a set of points on a hemisphere of radius 1 centered at the origin, where the antipodal points on the equator are regarded as equal. So let's draw a picture of that. Okay, and then I want to draw a hemisphere. So 1 unit, 1 unit, 1 unit, 1 unit, like that. So this is kind of in the background. Like this, coming around like that. Okay, so there's a hemisphere. So if you give me any point in space, so here's your point ABC, draw a straight line through the origin, and at some point it penetrates that hemisphere, and it hits it at a unique point, going up to this point right here. And so you scale down the point ABC and you get a unique representative on this upper hemisphere. Then the points at infinity, those are the points where the z-coordinate is 0, would correspond to points on the equator. So these are the points at infinity, AB, 0. And because of the equivalence relation, this point AB0 is equal to the antipodal point over here. So this would also be, well, it's the opposite, minus A minus B 0, but the point is that in the projective plane, AB, we're using colon notation, won't we? So in the projective plane, A colon B colon 0 equals minus A colon minus B. They're just scalar multiples of one another. So you think of the points at infinity as being these points on the equator right here. Okay, and the finite points are all the points on the upper hemisphere. So that's a nice way to think of it. So every finite point has a unique representative on the upper hemisphere, while every point at infinity has a unique representative on the equator. Now, to define a curve on the projective plane, we have to start with a homogeneous polynomial. So what do I mean by that? So a polynomial in 3 variables, x, y, and z, is called homogeneous of degree d if every monomial has total degree d. So in the first example, every monomial has total degree 2, so this would be homogeneous of degree 2. It's also called a quadratic form. The second example, every term is homogeneous of total degree 3, and that would be called a cubic form. So a curve in the projective plane is the set of points x, y, z satisfying a homogeneous polynomial equation f of x, y, z equals 0. Now, why is this going to be a well-defined concept? So you have to think there's many different ways of representing points in the projective plane. So I need to make sure that if one of those representatives makes this polynomial equation 0, then any other representative will make it 0 as well. Well, why is that? If f of x, y, z is 0, and you multiplied x, y, z by a scalar lambda, well, because it's homogeneous, you can just factor out a lambda to the dth power. So just come up to, say, the second example. If you multiplied every variable by lambda, you'd have a lambda cubed here, you'd have a lambda cubed here, a lambda cubed here, and a lambda cubed here. Pull it off to the side, and because of f of x, y, z being 0, this quantity is still 0. So it doesn't matter which representative we choose. And for the same reason, you can only work with homogeneous polynomials when you're defining a curve in the projective plane. Okay, let's look at some examples. So here's a quadratic polynomial, x squared minus y squared minus z squared equals 0. And I want to describe that set of points in the projective plane. So we've got the finite points. So here we set z equal to 1, and we would have x squared minus y squared equals 1 squared, and we all recognize that this is just a hyperbola with asymptotes x squared equals y squared, so x is plus or minus y. Okay, let's draw both models like this. So in this model, we'll do it on the z equals 1 plane. Okay. And just sketch this hyperbola. So this is think of this as being the x-axis up here, and this is the y-axis. And so this hyperbola has these asymptotes, x equals plus or minus y. I don't know that I would want to draw those in right away. Let's see which variable is restricted. So x squared is 1 plus y squared. That means x in absolute value is always at least 1. There's 1. And so it's a hyperbola like this, something like this. Okay, so those are the finite points. And then we have the points at infinity. So you set z equal to 0. And this time we get x squared minus y squared equals 0, x squared equals y squared, x equals plus or minus y. And you'll say, oh, those are the asymptotes. So the points at infinity correspond to the asymptotes of the curve drawn in the finite plane. So what points are these in the projective plane? So you would have the z coordinate is 0. Let's set the y coordinate equal to 1. And so we can have x to be plus 1 or negative 1. So this curve has 2 points at infinity. 1, 1, 0. So 1, 1, 0 right here. And negative 1, 1, 0. Negative 1, 1, 0 over here. Now let's draw it on the hemisphere model. Draw a hemisphere. Yeah. Like that. Okay, good enough. And let's draw these points at infinity. So 1, 1, 0. It's right here. It would actually be scaled down to fit on that unit circle. And this also equals this point right here. This is also 1, 1, 0. And then we have negative 1, 1, 0 with these 2 points. Remember, those are the equal points in our projective model. And so what is the curve going to be doing? So this curve right up here is going to do something like that. Okay, so let's draw some color. So that corresponds to this part. So notice what's happening then. As this curve goes off to infinity, you are actually approaching these points at infinity along the equator. And then there's a second branch, this one over here, and that's kind of on the opposite side of the sphere, so it's kind of coming up like that, on the back side, like that. And it looks like the original hyperbola has 2 different components. But look what happens in the projective plane. You're traveling along the curve like this. You get to the point at infinity right here, but this point equals the antipodal point in the back. So you've turned the hyperbola into one continuous loop. So it's as though you are traveling on the hyperbola like this. So you go out to infinity, and as soon as you reach infinity, you come back along this part of the hyperbola. Then you're going off to infinity and coming back over here, and it's just making one big continuous loop. Now, I want to talk about homogenizing a polynomial. So we start with just any polynomial in 2 variables of degree d. And to homogenize it, I throw in a third variable z that will make every term of the same degree. So you throw in whatever power of z you need so that the given term has the degree of the original polynomial. So if the original polynomial has degree d, you'd want to put in z to the d minus I minus j. so that when you add the 3 powers, these 3 exponents add up to d in every term. So note that f of xyz is a homogeneous polynomial of degree d, defined in this manner, since I plus j is always at most d, and when we add up the 3 degrees, it adds up to d. You can also note that that the original polynomial can be obtained just by setting z equal to 1. So let's look at an example then. Take the polynomial f of xy equaling x squared minus y squared minus 1. So in R2, the curve defined by this polynomial is simply the hyperbola x squared minus y squared equals 1, which has asymptotes at y equals plus or minus x. When I homogenize the polynomial, I want to throw in a new variable so that every term has total degree 2. So this term right here, I'll just multiply by z squared, and we get the polynomial capital F of xyz is little f homogenized, and that's x squared minus y squared minus z squared. And so you can think again in the example we looked at first, we took the hyperbola of points, just the ordinary finite points in the xy plane, and by homogenizing the polynomial, we obtain a collection of new points at infinity that we get to add to the original polynomial. And in this case, there were 2 new points at infinity that we got to add to the polynomial. Okay, let's return to our elliptic curve now. So an elliptic curve is defined by an equation of this type: y squared minus this cubic polynomial, such that this equation is non-singular. So this cubic polynomial can't have any multiple zeros. When I homogenize that equation, I want every term to have degree 3, because this is a polynomial of degree 3, the maximum degree. So I throw in a z on the first term, so I get y squared z. I leave the x cubed alone, and I add a z to the x squared term. I add z squared to the x term, and then I put a z cubed on c. So now every monomial has total degree 3. And so let's describe what the projective curve defined by capital F looks like. And so again, we've got finite points. These are the points where you set z equal to 1. And those are just the original points. So when you set z equal to 1, you're just hitting the ordinary elliptic curve, elliptic curve. Y squared equals x cubed plus ax squared plus bx plus c. And then we've got the point at infinity. Here we set z equal to 0. So when I set z equal to 0, I'm going to get 0 minus x cubed plus 0 plus 0 plus 0 equals 0. We get the simple equation x cubed equals 0, which means that x equals 0. So in the projective plane, the only point satisfying the equation f of xyz equaling 0 at infinity is this point where both x is 0 and z is 0. And so y has to be a non-zero value, and it can easily be then scaled to be a 1. We get a unique point at infinity. So this is the only point at infinity on the curve f of xyz equals 0. And that is our point P infinity that we were talking about in the last lecture. So let's look at this model just on the hemisphere this time. One. That. Draw our point at infinity. 0 in the x, 1 in the y. Here. And that's equal to this point. And then we have our elliptic curve. So you can think of it as living up here on this z equals 1 plane like that. And let's do it the example we did originally. So it was an elliptic curve that would come around like this. Something like that up in the finite plane, and then you want to project that onto the hemisphere. So what are you going to get? You're going to have the curve approach this point at infinity. Let's thicken it up. It's then going to wind behind the kind of go on the opposite far side of the hemisphere. That's when x becomes negative. Got dotted right there. Then it's going to come back around and approach our point at infinity. So something like that. So this elliptic curve then, as you go off to infinity, on the elliptic curve, you're just approaching these points, this single point at infinity. And so once again, the elliptic curve just becomes a single component because these 2 points are identified right here. Now let's look at this concept of drawing a line between 2 points on our elliptic curve. So this is how we define addition of points. We would draw a line segment joining 2 points and then look at the third point of intersection. So what does a line look like in the projective plane? So the equation of a line is something like this: ax plus by equals c. When you homogenize this, you get ax plus by equals cz. That's the equation of a plane passing through the origin. And so now if we look at the hemispherical model, let me again draw a picture of it down here. So here's the hemisphere model of the projective plane. So if you have a plane passing through the origin and you intersect it with the upper hemisphere, what do you get? You get a great circle on the sphere, something like this. So a great circle is what a straight line is viewed at in this model of the projective plane. Okay, now, what was the problem we had with our elliptic curve before? So we had problem with vertical lines. when we had vertical lines joining 2 points on the elliptic curve, we said, well, there's no other point where it intersects the curve. So we threw in this point at infinity. So what does a vertical line look like in this model? So on a vertical line, b equals 0. So a vertical line is just an equation of the form ax equals c. X is a constant. So b is equal to 0, and so your equation is just ax equals cz. And one point in particular that will always satisfy an equation of this type is when both z and x are 0. So any vertical line will pass through this point 0, 1, 0. So here's my point 0, 1, 0 in the projective plane. And so vertical lines are really to be thought of as great circles passing through this point. And what is that point again? Well, look at our previous slide. That is the unique point at infinity on the elliptic curve. So every vertical line passes through this point at infinity. And what happens when we draw vertical lines? So it's a great circle on the hemisphere. It hits the elliptic curve at these 2 points, which are symmetric about the x-axis. So a vertical line passing through those 2 symmetric points will also pass through this point at infinity. And that's how we make rigorous this addition law we defined before. So you really, to formally define the elliptic curve, you want to think of it as the set of points in the projective plane where you've added this additional point at infinity, and your lines and chords correspond to doing this type of intersection with these great circles.